flow between parallel plates. Probably the simplest non-circular duct flow is fully developed flow between parallel plates a distance of 2 each, as shown in this picture. Flow between parallel plates, as we said, this figure with the dimension of B 2 much greater than H, and the plate are the distance of 2H as shown in this picture. So the flow is essentially two-dimensional. That is, say that we have a velocity distribution in y direction. The hydraulic diameter is that is twice the distance between of the plates. So let me write again the hydraulic diameter is 4H. Twice of the distance between two plates. The pressure gradient is constant. Where L is the length of the channel along the x-axis. L is the length of the channel. Channel along the x-axis is shown in this direction. Laminar flow solution. There is formulation for laminar flow. The laminar solution was given in section chapter 4 in connection with the a control value. We can write for an flow between two parallel plates, obtain this relation on H2, where the maximum H2 on 2 mu Q equals to 2BH3 on 3 mu delta P on L. We have also a relation for V Q on A. These are the formulation for laminar flow between two parallel plates with 2h distance. We have also relation for the shear stress on wall at y equals to h hf Now use the head loose to establish the laminar friction factor F laminar on DH, B2 on 2G. Mu 96 on DH. Thus, if we could not work out the laminar theory and choose the use the approximations F equal to also this DH, the hydraulic diameter approximations is relatively crude in laminar flow. The next modeling, the next approaches in the turbulent flow in the duct flow, non-circular duct flow is turbulent flow solution for two parallel plate ducts. For turbulent flow between parallel plates, we can again use the previous equations available in this chapter, which said that for the entire channel, using not y but a wall coordinate y, you can use the relation logarithmic law on viscous friction velocity and nu plus v. The distribution look very much like the turbulent profile for pipe flow in the previous example solution, and we can obtain the velocity as a relation of between two plates u y, which can calculate friction velocity recalling that V on U star equals to we have that the relation for we see that from this equation is equivalent to a parallel plate friction law. Rearranging and cleaning up the constant term, we can obtain the relation for friction factor in this type of duct. Where we have introduced the hydraulic diameter dh 4H. This is remarkably close to the smooth wall pipe friction law. Therefore, we conclude that the use of the hydraulic diameter in this turbulent case is quite successful. That turns out to be true for other non-circular turbulent flows also. This equation can be brought into exact agreement with the pipe law by rewriting in the form of we have Reynolds modification hydraulic diameter, the friction factor minus thus the turbulent friction is predicted most accurately when we use an effective diameter differential. Reasonable accuracy. Laminar theory. Better accuracy. For calculating the turbulent friction in ducts. In ducts, Jones show that the effective laminar diameter idea collapses all data for rectangular ducts of arbitrary height to width ratio onto Moody chart for pipe flow. We recommended the Moody chart for any height to width ratio. End of this section. The next section is about flow through a concentric anode.